Hi everybody, welcome back. In this video we're going to be talking about randomized control trials, building on our last videos, econometrics videos, talking about the goals of the goal and challenge of econometrics, being the elimination of selection bias that arises from unobservable differences. And remember last time we saw a table and we're kind of using an example of health insurance. And we initially started out seeing that we saw that some people with health insurance, or that the people with health insurance have better stated health outcomes on a scale of 1 to 5 than the people without health insurance. But in order to find a causal effect, we need to make sure that everything else is equal across both groups and that there's no what we call selection bias or selection effects, that certain types of people select into having health insurance and some people don't. And as we see, based on a number of different characteristics, but particularly educational levels, employment, and family income are not nearly equal among the two groups. And we do have some selection effects that the people who are more likely to have more education, they're more likely to be employed, they have higher family incomes. These people are also more likely to have health insurance. And we would also expect that these traits would also be correlated with higher levels of health. And so because these are not equal among both groups, we can't claim any causal effects by comparing these differences in the stated health up at the top. So we need to remove selection bias, and the best way to do that is through random assignment. Okay, and what random assignment is, or what it does, is that it eliminates all selection bias if done properly. So it eliminates all selection bias. And the way it works is you start with a sample of people who are uninsured. If we're going to use our current example, start with a sample of people who are all uninsured, then provide health insurance to a randomly chosen subset of this sample. Then provide health insurance to a randomly chosen subset. Oops. A randomly chosen subset of this sample. Okay, so start out everybody without health insurance. Randomly divide these people into two groups. So we have two randomly chosen groups. And when large enough, and this part is important, I'll discuss that in a second. When large enough, having two randomly chosen groups ensures that the comparison between the groups satisfies the ceteris paribus assumption. Two randomly chosen groups, when large enough, ensures that the comparison between the groups satisfies the ceteris paribus, or all things equal assumption. Okay, and this is due to, in statistics, the law of large numbers. Which we're going to abbreviate from now on as LLN. Okay, and this law of large numbers we can define as the larger the sample, the closer the sample average will be to the average of the population from which the sample is drawn. The closer the sample average will be to the average of the population from which it was drawn. So to kind of make this a little bit more clear, let's use an example first with dice, and then I'll talk about it in a normal context. So if we take the expected value of one roll of a die, a simple die, 6 sides, as we know, we can calculate that probability by looking at the individual probabilities of each event occurring. So we have sides 1 through 6, and any individual side I has a probability of happening of 1/6. So you have the event times its probability, and if you add up all those probabilities, if you add up all those probabilities, you get the expected value. So side 1 has a probability of 1/6, plus side 2, which has a probability of 1/6, plus all the way up to side 6, which has a probability of 1/6. And you add all those up together, you're going to get 3.5, which is strange. You can't actually have a 3.5 on a dice or on a die, but if you roll a dice a lot of times, the average of the numbers of all the rolls is going to end up being 3.5. And so if we actually did roll a dice, suppose we roll a dice 3 times. All right, what's the average? That could be any number of things. It's possible we could roll all ones. 1, 1, 1, an average of 1. But if we roll it 10 times, maybe we'll get an outsized number of ones. But if we roll it 10 times, we're probably going to start getting a few of the different numbers because they each have equal probability. What if we do it 30 times? What if we do it 100 times? The more times we do it, as we approach infinity, if we were to do it thousands and thousands of times, the average, as we approach infinity, the average will approach 3.5. And so that's the whole point. As we add more and more rolls, as the sample gets larger and larger, this idea of the law of large numbers, the sample, the average of the sample, is going to become closer and closer to the population average. And in this case, the expected value is the population average is 3.5. But it's very likely that with a small sample, the average is going to be, the average could be, 1.5, the average could be 5, the average could be 4. With a small sample, there's much more variance and a larger probability that we're not going to roll, something that's going to result in an average of 3.5. But as we roll more and more and more, the average is going to approach 3.5. Okay, and so if we think about this in the context of a randomized control trial, we have the following. So when the subjects are divided randomly into treatment and control groups, when the subjects are divided randomly into treatment and control groups, they come from the same underlying population. Okay, and so again, through this law of large numbers, LLN, law of large numbers, if the sample is large enough, those in the treatment and control groups, treatment and control, T and C, those in the treatment and control groups will be similar in every way except the treatment. Okay, and so to kind of give you an example here, let's suppose that looking at gender, we would expect to see a similar proportion of men and women we would expect to see a similar proportion of men and women in randomly assigned treatment and control groups. So to give you an idea, let's say that this is the entire population of the study we're interested in, and let's say that out of that population, 50% are men and 50% are women. And let's say that the population that we're interested in studying is some group of, let's call it 100,000 people. So that means 50,000 each are men and women. If we take a small sample, this is a population, and this is the sample. If we sample 10 people and we do it totally randomly, So we have, either a computer program, or you could just think about it as flipping a coin. Heads, you're in the study. Tails, you're not. If we did that, it's possible if we only took 10 random people, it's possible maybe 8 of them are men and 2 are women, and it's not close to the underlying population. But if we take a larger sample of, say, 50, we might still not be exactly perfect. We might not be exactly equal. Maybe we have 40 men. Oops, that's not adding up to 50. Let's say we have 20 men and 30 women. But the law of large numbers, as we have larger and larger samples, the sample average is going to get closer and closer to that population average. If we randomly select 100 people or 1,000 people, maybe we'll have 500 and let's call it 510 men and 490 women. It's not going to be perfect, but it's going to be a lot closer to a 50-50 split. And so the larger that sample gets, the larger the sample population, or the people in the sample resemble the underlying characteristics in the population. Same could be said, it doesn't have to be something that's 50-50. You might have something that's, let's call it 5% of the people are economics majors and 95% are not. And let's say that's a random sample of 20,000 students. If you're interested in doing some study to look at how different majors affect something, or you want to make sure you have the same proportion of people in a certain major, again, make sure you get a large enough sample size. And as you're really approaching kind of 30 plus, it really depends a little bit on the underlying population, but 30, 50, the more the better. If we had 100, maybe we'll get 4 in here, maybe we'll get 6, but that's going to be 5%. So if we had 6 people and 94, it's not going to be right on, but as this sample gets bigger and bigger, we're gonna get increasingly closer to matching our sample average to the population average. So the important thing about this is that not only is this going to be true in things like gender and education and, say, the age breakdown of all the individuals in the two randomly assigned groups, but with a large enough sample, and this is kind of the key, with a large enough sample, not only will the observable characteristics start to resemble the underlying population, but critically, the unobservable characteristics. These are also going to be similar in the sample as they are to the underlying population. A couple examples here could be something like work ethic, very hard to measure, or motivation, or just generally inherent ability. These are all hard to measure very directly, but let's say motivation. It's kind of a weird thing to measure, but let's say that if we have people of high and low motivation, and let's suppose that 20% of all people in the whole population, 20% of people are high motivation, 80% of people are relatively low. So high, low, and that's call that a population of 300 million people. I don't know the real numbers. Maybe I'm thinking people are here. Let's call it a third a third of the people are highly motivated, and 2/3 are less. Again, it's hard to say because it's hard to measure. But if there was some dichotomy like this, and you took a sample of 100 people, even these unobservable characteristics are going to start to be the same between the sample compared to the population. So with 100 people, maybe we'll end up with 30 people who are highly motivated and 70 people who are not. We're not straight at 33% and 67%. But again, as that sample gets larger and larger, we're going to approach the averages found in the population. It's true for observable characteristics. It's true for unobservable characteristics. Okay, and that's the critical piece about random assignment. So random assignment combined with the law of large numbers removes selection bias by ensuring that the mix of individuals being compared is the same. By ensuring the mix of individuals being compared is the same. Okay, and so, yeah, so we're going to have two groups. We're going to have a treatment group. Well, we have ultimately the underlying population. And from that, we're going to have two groups, treatment and control. And on all sorts of observables and unobservables, if these two groups are truly random, so we randomize who gets the treatment, we randomize who gets the control, and again, as long as these groups are large enough from the law of large numbers, we're going to have groups in both the treatment and the control. So all of these little random things are just different characteristics. But with a large enough little bit of artwork here. So, these could be age, race, gender, all sorts of demographic variables, all sorts of educational variables, economic variables. But essentially, with the law of large numbers, these treatment and control groups both will resemble the underlying population. The only difference between them, here we go. The only difference between them is that one group gets a treatment and the other group does not. So there's nothing here, but there's a treatment for this group. So this group, we're going to give them a treatment and we're going to see what happens. Otherwise, they look identical to each other because they were taken as random samples from the underlying population we're interested in studying. Okay, and so I'm going to actually pause it here, and then what we're going to do in the next video is look at how researchers in the past have used an excellent randomized trial in the healthcare market to actually try to find out the effect of health insurance on health outcomes. Okay, so that's going to be coming up next. I'll see you in that video. Thanks.